Hello, I am A/P Dr. Woon Kai Lin from the Department of Physics at the University of Malaya. In this video, we will explore the question, how does quantum physics affect our everyday life? We will be comparing classical intuition with quantum reality, looking at the rules governing the universe and what happens when they break down at the quantum level. The golden rule of classical physics is the conservation of energy. Energy cannot be created nor destroyed, only transformed or transferred. This means the total energy of an isolated system remains constant over time. These deterministic rules govern the universe at a large scale. Whether it's a ball rolling in a valley or a satellite orbiting Earth, the underlying math involving the conservation of energy is the same. When we translate conservation of energy into the quantum realm, we use the Schrödinger equation. This equation expresses the total energy of a particle through kinetic and potential energy components. The ultimate question in quantum physics is an electron a particle or a wave? Based on classical intuition, if electrons are physical particles, shooting them through a double-slit partition should result in two distinct bands on the screen. However, electrons defy classical expectations. Instead of two bands, they create an interference pattern, suggesting that a single electron can pass through both slits at the same time. The electron is both a wave and a particle. Remarkably, even when single particles are fired one by one, they gradually build a predictable, continuous wave pattern over time, demonstrating their wave nature. This wave nature is not limited to subatomic particles. Complex biomolecules, like the polypeptide gramicidin A1, also exhibit matter-wave interference, showing the wave nature of matter at a larger scale. We map the unseen quantum world using probability. The square modulus of the wave function is the probability density that a particle is at a specific location. Traveling wave packets illustrate a trade-off. Higher localization pinpoints position but obscures momentum. This trade-off is formalized by the quantum uncertainty principle. It sets a fundamental limit on precision, stating that the universe inherently blurs the exact position and momentum of matter simultaneously. A particle exists in a superposition state, meaning it can be in multiple states simultaneously. For the double-slit experiment, an electron exists in a superposition of passing through both slits until it is observed. Scaling probability to the macroscopic world is evident in the decay of radioactive nuclei, which is a strictly random process governed by its half-life. For example, plutonium-240 has a 50% decay probability after 6,560 years. Schrödinger's cat illustrates the box of overlapping realities. Since the decay of the atom is probabilistic, until the box is opened and observed, the cat exists in a mathematical superposition, simultaneously alive and dead. A core mystery of quantum physics is that the act of looking changes everything. If we place a detector to observe which specific slit the single electron goes through, what happens to the wave pattern? The mere act of observation forces the electron to choose a path, collapsing its wave nature entirely. By measuring the quantum realm, we force it back into the classical rules of particles. The observer is intrinsically linked to the fabric of reality.